Hi, everyone. Welcome to the ATIC seminar series. Today we have Peter Manohar with us. He's a fifth-year graduate student at CMU, advised by Guruswami and Pravesh Kothari. He has several cool works in coding theory, extremal combinatorics, algorithm design. Today, he'll be talking about his recent breakthrough result on locally correctable codes, which also appeared in the Quanta magazine. So yeah, it's over to Peter now.
Yeah, thanks for the introduction, Santoshini. Yeah, so today I'm going to be telling you about that paper and also, I guess, a recent follow-up we have to it where we're proving, again, better lower bounds for three-query locally correctable codes. And this is going to be based on joint work with one of my advisors, Pravesh Kothari, who was at Carnegie Mellon University with me and has now moved on to the IAS in Princeton. Okay, so let me just start off the talk by defining what locally correctable codes are. And so this is going to be an error correcting code. So it's a way to encode a k-bit message B into an n-bit string X. And for the purpose of this talk, every such encoding I'm going to think of as always being systematic, which means that the first k bits, you can see my cursor, right? Yeah, okay. So the first k bits of this encoding here are always going to be equal to the message B. So you encode by basically taking the k-bit message and then adding extra stuff on top. Okay, so a locally correctable code is going to give you some encoding map, and then we let our adversary come in and make an arbitrary delta n errors to this encoding X to produce some Y, and we want to be able to locally correct Y. And what this means is that we want there to be some local decoding algorithm that takes as input an index U and N, which specifies the bit of X that we would like to decode or like to correct. And then the decoder gets to toss some coins, and based on the output of these coins, can make at most Q queries to this string Y. These queries can be made adaptively, so that means that the decoder can choose to read an entry of Y, and then based on what the value of that entry is, that can defect the next query that the decoder makes, and so on. But as a whole, the decoder has to make at most, or has to read at most Q entries to Y, and then the decoder should output some X hat sub U, and hopefully this is equal to X sub U. So hopefully we indeed recover the true youth bit of the encoding. And so more formally, we'll just say that the code is Q delta epsilon locally correctable if, when given any Y that is within this delta proximity of a true code word, and for any input U, the decoder should always be reading at most Q bits of Y, and it should output X sub U with probability at least 1 minus epsilon. So delta is like the fraction of errors we can tolerate, and epsilon is the error probability of the decoder.
Peter, I have a question here. So why do we want to decode it at every location like U and N? Like, because you said the code is systematic, wouldn't it, suffice for us to consider U and K? Does it make a difference?
Yeah, so that's going to be actually the next slide, which is a different type of code called locally decodable codes, and they're very closely related. So yeah, let me maybe just continue a little bit and then I'll mention some of the differences. Yeah. Okay, so the definition, at least here, is clear what the definition is, and yeah. So, okay, so the reason you might care about local correction is it's very, very useful for a lot of different applications, such as things like program checking, probabilistically checkable proofs, private information retrieval schemes, and so on. And as Santoshini has mentioned, there's this alternate notion of local decodability where you just care about decoding the message bits. And actually, depending on your application, you might want either local decodability or local correctability. Sometimes in like probabilistically checkable proofs, you need to be able to correct all bits of the proof, which is like, you can think of as the encoded string, not the original message. So there's various things that come into play here. And yeah, depending on your setting, locally correctable codes or locally decodable codes might be one of them might be the thing you want to consider. And yeah, so the definition of locally decodable codes is basically the same. The difference is, I'm only trying to decode I and K, which is the K-bit message, rather than the whole n-bit string X. And yeah, I guess because I've said the code should be systematic, this clearly implies that local correction is the stronger property, because if I can correct all n bits here, in particular, I can correct the K bits here, which is the message. But other than that, the definition is identical, right? I just am switching like what thing I'm trying to decode. Okay, so I can just kind of toggle back and forth between these two. And as you can see, like the thing that is changing is just this, whether I'm decoding U and N or the message. Okay, so the first question you should ask is, do these codes even exist? And this is a purely combinatorial question. Usually in coding theory, you'll want to care about things like, can I construct the codes efficiently? Can I encode efficiently? And for LCCs and LDCs, even before we can get to efficient constructions or efficient encoding maps and so on, can we even show that these objects exist? It's actually non-trivial because unlike in standard models of error correction, where in those models you can show that there exist good codes by doing what's called a random coding argument. This is an old argument going back to this paper of Shannon from I think it's like 1947 or something, where basically he shows that if you just take a random code, it's actually a good code with high probability. But here there's no natural random probabilistic model to even sample these objects from. So yeah, it's even showing the existence of a code that is locally correctable is a somewhat non-trivial task. Of course, these codes do exist, otherwise I would not be giving a talk on them. And there's a very simple construction, which is the Reed-Muller codes. So these are going to be Q-query locally correctable codes for any choice of a constant Q. And they have a block length n that's 2 to the k to the 1 over q minus 1. So it's exponential, but you can get better codes if q increases. And since it's a Q-query locally correctable code, it's also locally decodable for free. So let me just sort of explain briefly how this works to give you a flavor of how you would construct such codes. So for 3-query locally correctable codes, what you do is you would take degree 2 polynomials over some finite field, let's say F4, and they're going to be multivariate polynomials in some number of variables t. And you take the set of all polynomials and then you evaluate them over the whole domain. So that's F4 to the t. And that is your encoding. So basically the message gives you the coefficients of this polynomial f, and then you encode it by thinking of it as a polynomial and evaluating it over this whole domain. And to decode, well, what you're going to do is use polynomial interpolation. So to decode a point f of z, what I should do is I'm going to pass a random line through z, and then just read the 3 other points on the line. And so I now made 3 queries. And by polynomial interpolation, if these 3 queries are not noisy, then I can, of course, just interpolate and get f of z correctly. And the other property you need is that for any z and any, I guess, z prime, there is a line going through z and z prime. So that way the distribution of any one of these individual red points on this line, if I pick a random line, is uniform. So if there's delta n corruptions, I have some order delta probability of hitting, like 3 delta probability of hitting by union bound a bad point. So therefore, with probability 1 minus 3 delta, I will miss all the errors and therefore correctly decode. Right, so it's a very simple construction. You can get a binary code. So this code was over F4, but you can get a binary code by just projecting down to F2 via the trace map. And if you go through the parameters, you can compute that there are about t squared over 2 degree 2 polynomials. And the block length of this code is 4 to the t because that's the number of evaluation points. And so then you get the block length is 2 to the order of square root k, but in particular, the leading constant is 2 root 2. So this was a very simple construction of codes. And you can imagine that if you use some more complicated algebraic techniques, you could in fact do better. So this is sort of like if I were to take someone who's done some coding theory and tell them form a locally correctable code, they'll probably come up with this in a couple of hours at most. So the question I want to ask now is, can we do better? So let me tell you the story. Let me wind back the clock 2 years and tell you the story as it was in 2022. So in 2022, what we knew was that for 2 queries, this code achieves a block length that's 2 to the k. This is also called the Hadamard code. And this is in fact tight. So there were some works in the early 2000s that proved a tight lower bound for 2-query locally decodable code, so even the weaker notion. And therefore, this implies the same bound for locally correctable codes. And we know that up to some constant of the exponent, this isn't deep tight. But for q equals 3, something a little bit more interesting happens. So for q equals 3, this is what I said was the best construction of a locally correctable code for read-more codes. But for locally decodable codes, you can actually do substantially better. So for locally decodable codes, these two works of Sergei Yakanin and then Klim Efremenko show the existence of a 3-query locally decodable code of sub-exponential length. If you look at this exponent here, this is like a 2 to the root log k. Let's ignore the log k. It's not that important. And remember, 2 to the order log k would be something polynomial in k. So this is something that's sub-polynomial in k. So this is like a 2 to the k to the little o of 1. So it's much, much better than this 2 to the square root k that we had for Reed-Muller codes. But this is the weaker notion of local decodability. And you can ask, like, can you even show that this code is, say, locally correctable? And turns out this is actually an open question. We don't know whether even this construction that we have, a very explicit construction, is even locally correctable. And in some sense, you should probably believe that the answer is no. And that's because when you're building these codes, you kind of build them in a way to make them either locally decodable or locally correctable by construction. And so if these codes are built to be locally decodable by construction, but they're not like obviously locally correctable, and if they're not obviously locally correctable, they are probably not locally correctable, but formally this is not known. So these are actually the two best constructions we know of for locally correctable and locally decodable codes. And I guess they're both linear codes. Pretty much all the constructions we know of for these codes are going to be linear. Yeah, and you can wonder how tight these constructions are. And so to show that these constructions are tight, we need to prove lower bounds. And the only lower bound we know is a very weak k-squared lower bound. This is a lower bound for 3-query locally decodable codes coming from this work of Carnegie and Wolf from 2004. And so we are very, very far from being able to show that either of these codes are close to optimal. And in fact, we even have some somewhat, I guess, formal evidence that is trying to argue that basically the techniques that we're using to prove these lower bounds cannot even go beyond k-squared. So there's somehow some barrier here. So just to summarize what I've said, I asked, can we do better? The answer is yes for locally decodable codes. And for locally correctable codes, the answer is we just simply don't know. And given that there's been actually quite a lot of work on trying to get better constructions of these codes, at some point, you might want to conjecture that perhaps we are failing because these codes are actually optimal. Maybe Reed-Muller codes are indeed optimal locally correctable codes. And we actually know that this is the case for Q equals 2. So this is not like a completely crazy thing to suggest. And for Q equals 3 or higher, there is something very interesting that happens, which is that there's some technical barrier to proving this. Well, more formally, this work of Barkola, Shai, and Weinreb showed this connection between a conjecture and design theory called the Hamada conjecture and proving that Reed-Muller codes are optimal. In particular, the Hamada conjecture is about constructing designs of some bounded rank, or I guess you want to maximize the co-dimension of the design. I'm not really going to go into what designs are, but essentially Reed-Muller codes give you designs, and designs give you locally correctable codes. In general, a locally correctable code might not give you a design. So designs are like a stronger property, but they are a stronger property that is satisfied by Reed-Muller codes. You can think of it as like just some extra regular assumptions that like you sort of query. If you're trying to decode Z, you're going to query any other Z prime almost uniformly and things like this. And like when you're trying to decode, you're not querying any pair of indices like Z1 and Z2 too often together and things like this. So there's got some extra properties in there that are not strictly necessary for local correction, but are ones that are almost very natural to assume. And at some level, the design case is almost like, should feel like the hardest case, I think. So yeah, so there's this conjecture here. And the thing is, if we want to try to prove either of these two conjectures, we're going to immediately run into a very big technical barrier, which is that all our lower bound techniques apply to locally decodable codes. And what I said was we actually have a construction of locally decodable codes, the matching vector codes, that achieve a block length that's sub-exponential in K. So if you're trying to prove these conjectures by using lower bounds to locally decodable codes only, you're going to not be able to go beyond this bound, and in particular, so you're not going to even be able to get close to something exponential in K. Okay, so this is the story in 2022. Now let me tell you what the story is in the present day in 2024. So I'm going to show a sequence of results, and I'm going to show them by plotting them on this diagram down here, where on the left I have this K squared. That's the best known lower bound from 2022. And on the upper bound side, we have 2 to the 2 square root 2K, the best construction from Reed-Muller codes. And in the middle, we have this LDC barrier, which is that if you're proving lower bounds for just locally decodable codes only, you're not going to be able to go beyond this bound. And down here, we have the K squared barrier, which is some technical barrier that we have some evidence that our techniques are not able to go beyond K squared. So the first result we have is that we show that locally decodable codes have a block length n that's K cubed. So this is a very modest improvement on this K squared, but nonetheless, it does go beyond this K squared barrier. And we did this with a somewhat substantially different approach compared to prior work on lower bounds for these codes. And you could hope that these techniques that we used, which are coming from the algorithms literature, could be potentially a lot more powerful and yield better lower bounds. And in the follow-up work, Pravesh and I proved that for linear 3-query locally correctable codes, they must have a block length n that's at least 2 to the k to the 1/8. So this, in particular, lies above this LDC barrier. This is exponential in K. And this has a few interesting consequences. So the first thing is that our techniques do not work for locally decodable codes. And this is, in some sense, obviously inherent because you cannot go beyond this LDC barrier without doing something different for locally correctable codes. Another interesting thing is this is the first time there's been any lower bound proven for a locally decodable or locally correctable, a locally correctable code that does not prove the lower bound by just saying a locally correctable code is a locally decodable code, and therefore we can lower bound locally decodable codes. So we're doing something fundamentally different for local correction, and we're using the fact that the code is locally correctable and not locally decodable in a very strong way. And this is obviously necessary to get this exponential bound. Okay, and this is also like the first time anyone has proven a better lower bound for LCCs than LDCs. Another corollary is we've proven that these matching vector codes are not locally correctable. This is something that's probably believed, but this actually proves it now, and we've done it through a rather indirect way. This could have actually been something that's not so hard to show directly because you have a very explicit code that you could just analyze directly, but we've proven this via this indirect route of showing that there are no good LCCs at all. And so we posted this paper maybe like last November, and then this has already been proved. So in February, a work of Tal Yankovitz appeared where he gets this up to 2 to the k to the 1/4. He's using essentially the same approach, but he has some very, very clever new ideas I thought were very, very interesting. Yeah, I mean, I think I'll talk briefly somewhere in the technical stuff saying like what exactly he does that's different, but he has some very cool new ideas. And then very recently posted late last week, work of Omar and Venkat got this up to 2 to the square root k over log k. And their approach is a bit different. So they still use the same core technical idea as our proof, but they go through a rather different execution of the proof where they go via some connection to something called a rainbow cycle in an edge-colored graph. And this is a connection that we had perhaps implicitly observed in our work on LDC lower bounds. And it's a connection that was made explicit in this work by Shea, Kothari, Mohanty, Munha, and Sudakov. So they go through this connection, and then they apply this rainbow cycle bound, which is from a breakthrough work in combinatorics from late last year by Alon, Bucic, Sauerman, Zakharov, and Zamir. And so in hindsight, with this rainbow cycle perspective, you can actually view our proof also as proving the existence of some type of rainbow cycle. And there is a difference. So our proof is proving the existence of a weaker form of a rainbow cycle compared to this work by ABSZZ. And in some sense, basically the main technical or complications coming from our proof are the fact that we are reproving some weaker form of this fairly difficult combinatorial statement. Yeah. And so concurrently with this paper, Pravesh and I also showed that design 3 LCCs have a block length n that's 2 to the square root k. I mean, there's a little of 1 in the exponent, but up to that, this is an explicit constant. There's no omega here at all. And so this gets up here. It is really, really close to the construction of Reed-Muller codes, which is 2 to the 2 square root 2k. So up to this 2 root 2 factor in the exponent, we've actually proven this Hamada's conjecture for 4 designs. And the interesting thing here is that, like I said, we're showing the existence of some weaker form of a rainbow cycle. And actually this work of ABSZZ has a pretty long discussion suggesting that their proof might actually be tight. And their proof is perhaps not the threshold you might conjecture for the rainbow cycle problem, and adds this extra log k here. So if the speculation in this paper of ABSZZ is actually correct, then this means that the rainbow cycle using the stronger notion could not hope to get up to the full 2 to the root k. So there's something very interesting going on here where potentially the fact that this approach here only requires some weaker notion of rainbow cycles might allow us to go all the way up to square root k, whereas this other approach gets stuck. On the other hand, this other approach is very modular and has this nice, very simple reduction, and it fits in like 2 pages to this rainbow cycle problem. And so if you could just improve the rainbow cycle problem by like this little extra factor, you would immediately get all the way up to square root k. Okay, so all these lower bounds I've said have been for linear codes, I guess with the exception of this 3 LDC lower. So if you want lower bounds for nonlinear codes, the best lower bound is still k cubed, in spite of all these improvements for linear codes. Of course, all our constructions are linear codes, so you might actually just be happy with linear codes or even design codes. All our constructions are designs also. But nonetheless, it's probably nice to try to prove good lower bounds for the nonlinear case as well, just to get the full picture. And so also in the same paper, Pravesh and I proved that for nonlinear codes, the block length has to be k to the 1 over 2 epsilon, where epsilon is the error probability of the decoder. So if your decoder fails with probability, say like 1 over 100, we're in particular going far beyond this k cubed. So it's still some polynomial in k, but it's a much better polynomial at the very least. And as you take epsilon to 0, we can get this up to something super polynomial in k. So we don't go all the way up to the exponential lower bound, and we in particular do not get close to passing this LDC barrier, but okay, I mean, it's still substantially better than this k squared that we had even 2 years ago. So yeah.
Sorry, what's the delta factor there again?
So delta is the distance, or like you're saying your decoder should succeed with probably 1 minus epsilon when there are delta n corruptions.
Oh, right. Okay. Yeah, makes sense. Thanks.
Oh yeah, I guess there's implicitly everywhere there's some dependence on delta, and delta is, usually think of delta and epsilon as both being fairly small constants. So yeah. Okay. So for today, what I'm going to do is I want to focus just on, for the technical part, on this exponential lower bound, because I mean, the other lower bounds all have basically similar ideas, and things just get more complicated, especially when you go to the nonlinear case. So I'll focus on this result, and I'm going to basically give you a high-level overview of our proof and some brief description of some of the technical steps and some of the core technical ideas. Okay, so let me first tell you the proof strategy. The proof strategy is going to follow the approach that we had in our LDC lower bound work, where what we're going to do is we're going to reduce the task of proving a lower bound to showing that a set of linear equations, or XOR formulas, are going to be unsatisfiable with high probability, where these XOR formulas are generated with some small amount of randomness. Effectively, what we're doing is we're creating an XOR instance for every possible choice of a decoder, and the XOR instance encodes the fact that the decoder should succeed on a valid code word. So if you can prove that for any choice, you fix your decoder, that gives you the XOR instance, and if you can prove that with high probability over a random message, there is no code word X such that the decoder will decode, then you've proven that there is no code, because you've shown there's no way to encode a particular message B, or a random message with high probability is not encodable. So once we have this reduction, what we can do is now we can use algorithms that we have for refuting constraint satisfaction problems. Particularly, we can use these algorithms recently developed in some of my work and some other work with Jackson Abascal and Pravesh and Venkat that show how to refute semi-random instances of constraint satisfaction problems, where semi-random means that the instance has a very small amount of randomness. And this should be contrasted with, say, fully random CSP refutation, where the instance is generated uniformly at random from all possible instances. And what I want to point out is this application of this algorithm is not a black box application. The instance we produce from the LCC or LDC is not going to be semi-random, but these techniques are sufficiently robust to this sort of thing, and we can just nonetheless use the same algorithmic ideas to argue that these instances that we produce from the codes are actually unsatisfiable. So this approach here is in some sense inspired by some ideas that we've seen from the SAT solving community on the practical side. So I want you to think of this as some theory analog of the approach of using SAT solvers to prove theorems. This is something that people sometimes call like automated reasoning or something like this. And what they do here is they take a theorem and they encode it as a SAT instance, which is going to be some finite family of finite size SAT instances. And then what you can do is you can feed this into a computer and run actual code to then try to figure out if your theorem is true or not. And what we're doing is some theory form of this, because the instances we produce there's an infinite family of asymptotically large instances. So it's not like I can just put this on my computer and see what happens. But we can nonetheless use the sort of similar high-level approach where we use an algorithm for proving the theorem. And so, yeah, there's not really like a one-to-one connection, because this SAT solving approach is like a practical thing where you're actually running code. But I think nonetheless, our approach is inspired by this very cool idea coming from that community. For today, though, I'm going to present the proof a little bit differently. So I'm going to present the proof as a reduction from a 3-query locally correctable code to a 2-query locally decodable code. And the reason for this is that the spectral refutation approach using I guess these algorithms use random matrices and so on, is nice and has a lot of intuition. In fact, all the intuition I have for the proof comes from this perspective, but it adds a lot of notational baggage and things that are perhaps in a talk sometimes, just don't want to maybe add as much notational baggage. And so I think the 2LDC reduction is something that's easier to convey. So I'm going to present the ideas like this, but I think if you want the intuition for the proof, you should really think of it in the spectral refutation language. Okay, so before I can get into the proof, I first have to tell you some more combinatorial way of viewing a 3-query locally correctable code. And this is like putting this code in some sort of standard form, which makes it a lot easier to think about and analyze. So I want you to think about like what the decoder can do when decoding a particular bit x sub u. So what should the decoder be doing? Well, if the decoder is non-adaptive, which it actually will be without loss of generality for a linear code, the decoder is basically just going to query some entries of the noisy string y, and it then will compute some predicate on the answers that it receives. And this is like I haven't really said anything that deep here. Right, if the decoder is non-adaptive, it essentially has to do this. This is like nothing else it can do. And for linear codes, you can imagine that the predicate should actually just be linear. So you can output this predicate y restricted to C will just output the parity of the bits on C. And if you want to understand some structure in the query sets, the fact that the code is locally correctable implicitly means that these query sets C have to be somewhat like evenly spread over the full code word, or at least some constant fraction of the code word. Because if they were sort of concentrated on any particular bits of the code word, you could imagine those bits would be corrupted, and then you would not be able to correctly decode, right? So without loss of generality, it turns out that you can assume that these query sets form a hypergraph. There's a hypergraph H sub u per u. So these are the query sets you would make to decode X sub u. And you can assume that these hypergraphs are matchings, meaning that the query sets are disjoint. And it's going to be a 3 uniform matching because we're making 3 queries. So the size of each C is 3. And there should be omega n hyper edges because these hyper edges should cover some constant fraction of the total code word. So to just visualize this, I can have here some encoded string X. And here the HU has 4 hyper edges, C1, C2, C3, and C4, which I've colored down here. And as you can see, each vertex in the encoded string gets at most 1 color because this is a matching, so these hyper edges are disjoint. This bit here, 0, appears in C1, and it does not appear in C2, C3, or C4. This matching need not be perfect. So some of these bits here are uncolored. They don't belong in any hyper edge. But nonetheless, as you can see, a constant fraction of this whole code word belongs to some hyper edge. And so what the decoder will do is, without loss of generality, you can assume it's just picking a uniformly random hyper edge for one of these 4 hyper edges. So like, let's say it picks C1, so it queries then these 3 bits and outputs the parity of the bits, which is 1. Okay, is the description?
I have a question. So why should they not share a vertex? Like, I'm a little puzzled why the query sets form matching. Can you explain?
Sure. So imagine every query set shares actually this first bit here. Let's imagine we're in an extreme case. Then what could happen is, what you should do as an adversary to make your decoder fail is you should flip this bit, right? And then every hyper edge will make a mistake, and you'll be wrong with actually probability 1, and that's really bad, right? So you're clearly not locally correctable or decodable or whatever.
Okay.
So then the word,
sorry. So matching is sort of like for proving a lower bound, this is like the worst case or something, because this is
essentially, yeah. I mean, basically, the real thing is like the query should somehow be like smoothly distributed over all the entries of the code word. And then in like the extreme case, the smoothest case is a matching, and you can kind of just reduce to this case without loss of generality. Yeah. But essentially, if you think of the query sets as being sort of evenly distributed over the whole code word, that's effectively the same thing. And you can make the whole approach work with using what's called a smooth hypergraph. And in fact, in the nonlinear case, this is what you have to do, and it gets a lot more complicated. But in the linear case, you can assume it's a matching. I don't know. I think this is like a nice combinatorial description that makes things a little bit easier.
Yeah, I have a quick question.
Yeah.
So at the start, you said that we could be adaptive with our queries. Here, it doesn't seem like you're not being adaptive by choosing these query sets in advance. Am I missing something?
No, you're not. For linear codes, you can make them non-adaptive pretty easily.
Okay.
For non-linear codes, you have to use the fact, I mean, they're adaptive, and you can't make them non-adaptive. Well, you can make them non-adaptive pretty easily, but you lose a lot in that completeness parameter epsilon. So to get the good lower bounds, we can't actually do this, and we have to do something a lot more complicated.
Okay, so this is like specifically for linear codes, things work out nicely.
Yeah.
Okay, thank you.
Good. So an alternative viewpoint here is we can think of these hypergraphs as defining what's called the parity check matrix of a code. So the parity check equations of a code are basically a system of linear equations, and then your code words are the set, I guess the linear subspace that satisfies all these equations. They're like going to be homogeneous linear equations. And so basically for each choice of U and each hyperedge C, we want xv1 plus xv2 plus xv3 to equal x sub u for all code words x. Right, and this just means that if I XOR these 3 bits here, I'm going to get x sub u. And so this is a parity check equation. And yeah, I guess we have some number of like omega n squared of these equations because we have, n of these hypergraphs, each having omega n edges. So we have a lot of parity check equations, way more than, if you have like less than n, then by some dimension counting argument, you have good dimension. So here we have far more constraints than, like, I guess if these constraints were random, you would have no dimension. You would have like you would only have the trivial solution, basically. So do we need, I guess to have a code, or LCC, you need to have a lot of these parity check equations, and you have to choose them very, very carefully to make it so you don't lose all your dimension. So this is like going to be the starting point of the proof. And now let me try to explain this reduction. So we start with this parity check matrix, which is given by these hypergraphs H1 through Hn. And our goal is to construct a two-query locally decodable code of some length that's a bit larger. So n to the order L. L is going to be a parameter that we'll try to choose to be as small as possible. And then if you apply a 2LDC lower bound, well, the lower bound tells you that k, the number of bits in the message, is at most L log n. And so if I can take L to be, say, something like polylog n, then this quantity here, L log n, will be a polylog n, and then I will get like k to the 1 over c is at most log n, or 2 to the k to the 1 over c is at most n, and that's the lower bound. That's how you would get an exponential lower bound. So how am I going to construct a 2LDC? Well, I have to tell you some way to encode for every code word X in the LCC. I want to turn it into some code word Y in the LDC. And the encoding is, well, I'm going to explain the encoding at a high level because there's actually some very annoying technical issues that you have to deal with. But basically, the overall approach is going to be the following. We want to take X and map it to Y in this larger space n choose L, where we're going to identify n choose L with the subsets of n of size exactly L. And then we just use what's called the direct sum encoding. We set Y sub S to be the parity of the bits XV for V and X. Okay, so it's just like a very, very straightforward encoding. And so the real question is, why is this a two-query locally decodable code? So it's going to be a two-query locally decodable code, kind of for similar logic to what I had on the previous slide for three-query LCCs. But basically what you want is to find matchings which successfully decode. So you want there to exist these matchings, M1 through Mn, now on this bigger set of n choose L, and they want to be a size at most, or size at least omega n. And it should be such that if I have an edge ST, remember S and T are now sets in this bigger space. If I have an edge ST in the matching M sub U, it should imply that Y sub S plus Y sub T is equal to X sub U for all code words X. If I take a code word, I lift it to this larger space, and then I look at Y sub S plus Y sub T, I should actually indeed recover X sub U. And you can think of this as like these matching, the edges here are like the two queries we would make to the locally decodable code, right? I'd query S, I'd query T, I get back YS and YT, and I add them together and I get X sub U. And if U was one of those first K message bits, then I would get the correct bit of the message that I was looking for.
So don't you just need like K matchings here because you're only interested in locally decodable code, or do you also get LCC or?
No, so you need K matchings for the LDC. For the LCC, I would need big N matchings.
That's true. Okay. Right.
So we're somewhere in the middle where we can kind of correct all the bits of the underlying code word X, but we can't correct all the bits of Y, so it's not like a locally correctable code. It's something like kind of in between. But yeah, I mean, formally to show it's an LDC, I only need the K bits, but we can get all N of them. It's all kind of the same argument, so just kind of do it all like symmetrically. It's kind of weird to like single out the first K bits as like being special in some way, which we in fact we do in the spectral proof, but that's, I don't know, it's like you'd rather the argument be as symmetric as possible, I think.
Sounds good. Yeah.
Yeah. So we just need to show that these matchings exist. And the way we're going to do this is we're going to define a graph G sub U where I put an edge S and T if this equation holds. And basically this equation here is some form of parity check equation. So what I want is that I'm going to add an edge ST if this equation here, which is this equation up here, is in the span, the linear span of those parity check equations that define my parity check matrix. More formally, we're going to want to find explicit ways to derive constraints to add these equations. So I will like explicitly show you how to argue that there are many such equations in our code. But we'll do that in a couple of slides. And then one thing I want to point out is we clearly need this graph to have large average degree. If its average degree is smaller than a constant, it's already, the game's up. We can't find a large matching because there just simply are not enough edges in the graph, right? And then secondly, if the graph is actually bounded max degree, we are done. if we have this large average degree. And that's because if you just run a greedy algorithm to find the matching will have, or you'll find will have size like d u times n, which is like the number of the number of edges in the graph divided by the maximum degree, which is if it's order order 1 times the average, will give you some divided by some constant, will give you an omega big N sized, I guess, matching. And then you'd be done. Okay, so if condition 1 holds and we have this bounded max degree thing, we'd be done. But this is actually going to be false. It's going to be false essentially, even if the matchings are random. This is like kind of an inherent thing that's going to be false for the construction of this graph. So this is like a real technical thing we have to deal with. And this leads us to the row pruning step, which is a step of some form that has appeared in this works on CSP refutation. It's appeared on the LDC lower bound. It appears here. This is always the main technical part of the proof. In some sense, this has to be where all the heavy lifting happens, because this is the step that proves that we're going to get a 2-query locally decodable code in the end. So like, in some sense, I'm doing some fairly generic things up front to get down to this row pruning step. And then this is the step that determines whether the approach actually succeeds or not. And if we can find this dense subgraph G prime sub u that has bounded max degree, then we are done, because we just kind of go, I mean, it's going to be dense, so it's going to have basically the same average degree here, but then it's also going to have a large matching by just this argument here, because the max degree is now bounded. And then we're done. So this is like the high level structure of the proof. And the 2 key technical steps are 1, showing that you have enough equations to argue that the graph has enough average degree, and 2, then do this row pruning step. And you kind of got to make the steps work together so that you get a full proof. Okay. So let me now explain this.
Just a quick question, sorry. So I still don't follow why, if the max degree is large, you're not able to extract matchings. Is it just that the greedy matching won't work, or?
The greedy matching doesn't, well, so we are going to show that this graph G sub u has a large matching, but what we're going to do is show that basically there's few vertices of large degree. So if you throw them out, you still have most of your graph left over, and then you find a large matching within that subgraph. Right? If like every vertex has very, if like some like half fraction of the vertices have like degree that's like, you know, like du to the like 1,000,000 or something, that's like much larger than the average degree, then you're kind of in trouble. But it turns out to not be the case. But showing this is hard. Like this is the main combinatorics and like a lot of the technical stuff in the proof. So this is not an easy thing to do. And this is in some sense like kind of necessary, because this is like the part where we're going to prove that make the whole proof work. So like, you know, this is going to have to do some hard work somewhere, and this is the step where it happens. Yeah. Okay, so let's talk about this average degree thing. So I'm going to call this the degree heuristic, because essentially what's going to happen is the average degree d sub u will depend on this parameter L. And as I make L larger, the average degree will go up. And essentially, we're going to want to set L to be at like the exact point where the average degree becomes like some order 1. Okay. And so what happens is I have this edge ST in my graph, and I said I have the edge ST if the sum V and S of XV plus sum of V and T XV is equal to XU for all code words X. And you can notice that if V appears in both S and T, then the symmetric difference, then V will cancel. And so the only vertices left are the vertices in the symmetric difference. So this is what I'm going to denote by S, X, or T. It's a set of vertices that appear in S or T, but not both. And in this way, I can think of these edges as being labeled by a set R, which is the symmetric difference. So basically what I could do is if I have a parity check equation that looks like this, I can then find all pairs S and T that have symmetric difference R and add all these edges. And I can think of these edges as being labeled by this R because there's some underlying constraint that is being lifted up now to this sets S and T. So you can compute for a particular choice of R how many edges are contributed to the graph, or how many, or I guess what is the contribution to the average degree. And it turns out to be L over N to the size of R over 2. Although this is actually not strictly speaking true. This is strictly speaking true. This is true if the size of R is even. If the size of R is odd, there are actually 0 edges for some annoying reasons. And this is actually the size of R being odd is what's going to cause a lot of technical headaches in the proof. But for simplicity, let's just say it's L over n to the size of R over 2, because I can construct a much more complicated graph where this holds even when R is odd. So now I can recall that I have constraints. I have parity check constraints. There are constraints that look like this, where C is the hyperedge in H sub U. And I have omega n of them. So I have quite a lot of constraints. And yeah, so now I can just use these constraints to be the choices of R and see how many edges I get. Okay. So I can compute the number of edges I get, or the average degree is going to be like L over n to the 3/2, because that's the size of the set here. I have omega n of them, so I have omega n. And this tells me my average degree is like L over n to the 3/2 times n. And I need this to be at least 1. So it tells me I need to set L to be like n to the 1/3. And then if I use my heuristic that k is at most L log n, I'm going to get some like tilde of n to the 1/3. And this is more or less the calculation that begins the proof that gives us this cubic lower bound for 3-quart locally decodable. There's still more steps to do there. I mean, you still have to make this row pruning and things work out, but at the very least, this is like the heuristic that's telling you that this way we're forming the graph is like you can't get L better than some threshold. So then if the row pruning step works, this becomes an actual proof. The row pruning step doesn't always work out, or at least there are cases I know where I don't know how to make it work. But yeah, I mean, this is sort of some heuristic calculation you could do to get a feel for what the lower bound you can possibly prove is. So we need to do something better now if we want to go beyond k cubed. And what we're going to do is we're going to use the fact that we really have n hypergraphs here. So down here, I only used H sub u, right? I only used one hypergraph. Now I'm going to use all n of them simultaneously to derive a lot of constraints and then argue, well, for the derived constraints, the size of the set R is going to go up, but I'm going to make many, many more constraints. And then hopefully this kind of density trade-off will break in my favor and I'll be able to take else. So let me now show you sort of the key idea here, which is going to be chains. So here's what I'm going to do. I'm going to take a constraint of the form xv1 plus xv2 plus xw equals xu coming from the hypergraph hu. And I'm going to think of one variable here in this hyperedge as being special in some way, which we can pick arbitrarily. Then I'm going to take a constraint coming from the hypergraph hw, the same w here and here. And then now that I've done this, it's kind of obvious what I'm going to do. I'm just going to add them together. And so now I get a constraint that's arity 5. The arity has gone up. But on the other hand, I've actually produced n squared of them. And that's because I have n choices here, roughly, for this edge. And then once I pick w, there are, again, like omega n choices in hw here. So in total, I get n squared. And you can just see what this does to your density. You can run through the calculation, and it turns out your average density becomes L to the 2.5 divided by square root n. And this tells you I can take L to be n to the 1/5, and I got something slightly better. I'm getting like k to the 5. So it's some small win. We've beaten k cubed. Okay, is this derivation process clear? Good. Okay. Because this is like the first core technical idea of the proof. I mean, right, strongly we're using the fact that we have all n matchings, because otherwise, if I pick a w, there might not be any hyperedges here to continue with. So like really using this fact quite strongly now. And okay, so we got a small win with taking 2 chains. You can imagine I'm going to get a big win if I take longer chains. And that's what's going to happen. We're going to just basically keep tacking on more and more links to this chain until we get some R steps. And we're going to get omega n to the R edges. The arity is always going to be 2r plus 1, which is always odd, which is kind of annoying, as I said earlier. And the reason for this is that you kind of always have these 2 exposed vertices in each hyperedge. And then at the end, you'll always have this one extra vertex left over, which is like the vertex where you would hook on a new chain or new link in your chain if you were to continue, but we're going to stop after R steps. Okay, but you can go through this calculation, and it turns out your average degree is like L to the R over square root n. And so this means you could hopefully take L to be n to the 1 over 2r and get k is at most n to the 1 over 2r. And this means if I take r to be log n, then this n to the 1 over 2r term is a constant, and I'm very, very happy. It turns out there's some extra polylog factors floating around here, but basically, once you go through the whole thing, we'll get something that's like k is at most log 8n. and therefore we get this big one. So that's how we show the graph as large average degree. We just are forming chains. So now I want to briefly discuss this row pruning step, which is the main technical part. And so the way we're going to do this is we're going to do the following.
I have a question.
Yeah.
Sorry, can we go back to the chains? So why exactly, so can you take R bigger than log n? Like, why stop at log n? Like, what's
So
the
L always has to be at least R for the way the LDC is constructed. And so remember, there's an L log n. So if L is R and you take R to be like n to the epsilon, you start losing. That's something.
I see. Okay.
Yeah.
Okay. Makes sense. Thanks.
So there's like a threshold where it's good, and after that it gets worse, so you don't take it above that.
Okay.
Yeah. Okay. Yeah. So I guess let's move on to row pruning. And the key point here is what we argue is that a random vertex has bounded degree with high probability. And so therefore the number of vertices with large degree is small. And if this high probability thing is good enough, I can throw out all the larger vertices and I'll still have almost all my edges left in the graph. And so we're going to view this as this probabilistic viewpoint of picking a random vertex. And what we can observe is that actually the degree of a vertex, S, can be viewed as a low degree polynomial in the variables that are the n variables that are the indicator vector or the indicators of like if V appears in S. So you have n variables that are going to be 0 or 1, depending on whether V is in S or not. And a random vertex is going to have those random variables be set to be like Bernoulli with LP being L over n, because that's roughly, if you take a set of size L, each vertex appears in S with probably roughly L over n. And so once we have this viewpoint of the degree being a low degree polynomial, and we're applying, we just need some concentration inequality for polynomials in Bernoulli random variables. And this is what's done in this work of Kim and Vu. So we're using this Kim-Vu style concentration inequality. It turns out we need to actually reprove it ourselves to get some slightly stronger form with some better dependence on the parameter R, which is like the length of the chains. We can't just use a black box thing, but the high level approach is basically the same. We're essentially using some high moment method here to prove this. And at the end of the day, this concentration inequality holds when L is at least log to the 5. It turns out that I've actually lied to you. The concentration inequality doesn't hold always. It holds if the matrix is if it's a design. If it's not a design, something weird happens, and we have to kind of start the proof over and do some more technical modifications, and that causes some log squared n loss. But in total, we get this log to the 5 plus this log squared, and then plus this extra log n coming from the LDC lower bound, which gives us a log to the 8th. And the approach of Yankovitz when rephrased in this language is that he's just observing that computing the second moments suffices to get this probability statement to work. And when you compute just the second moments, you don't lose as many log factors. And so it only requires L that's like log squared n. He also does some different approach for handling the heavy pairs, which only loses 1 log n loss. Although we also later realized that this log squared is actually us just being a little bit sloppy from Cauchy-Schwarz. So we could have had this be log and without too much difficulty either. So, but I think the real thing is the second moment trick, which is really, really clever, and it gets it down to log to the 4. And then finally, for designs, we show that we can actually take L to be log n. And it turns out this is actually non-trivial. You might be like a little bit worried that we've assumed something stronger. And so the reason we just get a better bound is because we assume something stronger. But it turns out that we actually did need to make some technical changes to the graph to make this work. Like the graph that we had constructed in this work and the one that Yankovitz uses is not sufficient to go down to log n, even when we have this stronger block design assumption. So yeah, I guess that's the main technical part of the proof. That's, I guess, all I want to say really about the proof. And yeah, so just to wrap up, let me talk a bit about some open problems. So you can wonder what happens when the queries go beyond 3. And essentially, when you do this density heuristic or degree heuristic thing, you can get something that's like L is n to the 1 minus 2 over q minus 1. This beats out the n to the 1 minus 2 over q that we get for q query locally decodable codes. So it suggests that you can kind of plug in q minus 1 into what's the best known LDC lower bound and get something a little bit better for LCCs. Although I don't know if this is perhaps like the most interesting thing to do right now because our LDC lower bounds are just not that good. So, I mean, potentially the correct thing to do here would be to first get the better LDC lower bounds, and then you can probably use this trick to get very good LCC lower bounds as well. You can maybe be wondering what we did for nonlinear codes. And basically what happens is we have to form these chains adaptively. What we do is we invoke the decoder for XU, and it makes 2 queries. And then it tries to make a 3rd query, but when it makes the 3rd query, we don't actually make the query. We just invoke the decoder for that 3rd index. And then this forms some chain that's adaptive because it depends on the answers of the queries that it's receiving. And there's some issue here where if your success probability is 1 minus epsilon, we're going to lose some factor if we invoke if we're doing like forming R chains, it's going to decay. And so this prevents us from taking length log n chains and getting an exponential lower bound. And in particular, an interesting thing here is unlike prior lower bounds for nonlinear LCCs or LDCs, we cannot use standard reductions because they lose too much in the success probability for you to form chains afterwards. And then in particular for nonlinear codes, as is kind of the case in prior work, we do need the full power of the spectral refutation approach. We can't do simple combinatorial reductions to LDCs. And again, I want to return to this conjecture that Reed-Muller codes are possibly optimal linear 3 LCCs. We almost know that this is true. We know it's basically true in the design case up to this 2√2 factor. And we also know that it's almost true up to this root log k factor for general linear codes. And yeah, I guess getting up to root k is potentially interesting depending on whether this rainbow cycle problem can just be improved all the way, improved a little bit, or whether there's something really new needed to be done there. But I think the more interesting questions are, can we get exponential lower bounds, at least for nonlinear 3 LCCs? Because right now we're actually kind of rather stuck at this quasi-polynomial, k to the log k type thing. And finally, can we beat k cubed for 3 query locally decodable codes or 4 query locally correctable codes? And even in the linear case, this would be obviously quite interesting. So yeah, I think this is probably a good place to end the talk. If you have questions, just, I guess we can ask. Thanks.
Thank you. Let's thank the speaker. I'm stopping the recording.